Let me now consider a game where the strategies are continuous. Okay. So consider a very classic game in game theory, which is called the ultimatum game. Ultimatum game. It's a two-player sequential move game, and the first player has say rupees 100, and the first player decides. So player 1 has rupees 100, is given this, suppose that's he is given rupees 100, and he has to decide how to share it with another player. Call it player 2. Okay, so player 1 decides how much of rupees 100 that he can keep for himself, and how much of rupees 100 to give to player 2. Okay, so player 1 decides this division of this pie. Okay, player 2 observes this division, can say yes or no. So player 2 can accept or reject the proposed division. Okay, if player 2 accepts, then they sort of share it accordingly. If player 2 rejects, then both get 0. Okay, both get 0, so 100 rupees is gone, then payoff is 0 for player 1 as well. So that's the game. So it's called an ultimatum game. So here notice the strategy is continuous for player 1. For player 2 it's discrete, player 2 can say yes or no, but for player 1 it's a continuous strategy. Any number between 0 and 100. So say player 1 chooses P, where P is the share that he keeps for himself, and 100 minus P is the share for player 2. Okay, so and P can be any number between 0 and 100. Player 1 can choose to keep 0 for himself or up to 100 for himself. Okay, how do we depict this kind of game in extensive form expression? So the way we do it is write a cone like this. So player 1 first moves, player 1 chooses P, so we write P here. So P is a continuous variable that moves from 0 to 100. Okay, so it basically says there is no two. It's not saying that there are two choices, 0 or 100. By making this cone shape, we are saying any number between 0 and 100 is a strategy for player 1. Okay, and then we sort of pick a middle point here and say draw a node where we say player 2 is moving and it's saying yes or no. Notice that player 2 has an option to yes or no for every choice of P, but we are not drawing nodes for all possible choices of P. We are just drawing an one representative node for player 2 and depicting its options for any given choice of P. Okay, and 2 can accept or reject. If reject, then payoff is 0 0. If accept, it's P, player 1 gets P, player 2 gets 100 minus P. Okay, so this is how you depict an ultimatum and a continuous strategy extensive form game. Sorry, continuous strategy sequential move game using extensive form expression. Okay, so what will happen here? What would be the strategy? You can apply backward induction here. Notice why? Because Here all nodes, all information sets are singleton nodes. Okay, there is, everybody knows where exactly they are located, because 2 can see what 1 has chosen. So if suppose here, for any p positive, 2's payoff is 100 minus p. Okay, so as long as p is less than 100, this number is positive, so 2 would choose accept, right? So 2 would choose accept for any p. So 2 would choose accept for any p less than 100 is a best response. For p equal to 100, it's, you can still, player 2 is indifferent, because then payoff is 0 0, whether accepts or reject. But then accept is a best response, right? So you can continue to have accept as the best response for all p's. And so player 2's strategy is to choose accept for all possible p's. Okay, notice here 2 has to specify an action for all possible nodes in which he gets to move, and there are lots of nodes. Even though I have drawn a representative nodes, basically for every p 2 can move, so 2's choice must be conditional on p. Okay, and so that's why I'm putting this condition here. So I'm saying that for any p less than 100, it's quite easy, because 100 minus p is positive, so 2 should choose accept, because that gives him higher payoff. But even for p equal to 100, the 2 is indifferent between accept and reject, so accept is a best response. And so basically that means that whatever one offers, 2 must accept. So 1 should offer basically 0. So 1 should keep, say, I would keep 100 rupees for myself and not give anything to player 2. Okay, so that would satisfy subgame perfect Nash equilibrium definition, right? Because it satisfies backward induction, because every time, because player 2, we are ensuring that player 2 is playing a best response in all possible nodes. Okay, if you make player 2 choose reject when p equal to 100, then that leads to again a technical problem, because one would like to maximize p. So basically one would like to keep as much of 100 for himself. So basically, but then given p is continuous, for you can keep making p higher and higher and make p closer and closer to 100, so you don't find a best response there. So that's why for p equal to 100, making 2 accept ensures that one has a best response, which is to keep everything for himself. If the game was a discrete game, meaning that suppose you can only pay in units of rupees 1, so either you pay rupee 1 or rupee 2 or rupee 3 up to rupee 100, so then it's fine. Then you would have a case where for p equal to 100, there is, one could have chosen r as another best response, in which case one would have kept 99 rupees for himself, and rupees would give rupees only 1 to player 2. Okay, but the idea is the same in both cases. The idea is that one would keep as much as he can, basically, and give base to nothing. Okay, that's would be the sub-imperfect Nash equilibrium. So here SPNE would be p equal to 100 is a SPNE of the game in when p is continuous. If you p make discrete, then it would be 99. The reason why this game is very classic, because when you actually play this game in experimental labs, as you can imagine, nobody plays this subgame perfect Nash equilibrium. People often, player 2 rejects relatively high offers. So when p is 70 or 80, so 2 is getting 20, even then in many cases people find that the player 2 rejects. Okay, so basically player 2 punishes player 1, but punishment is costly for player 2 himself. He is also not getting anything, right? So player 2 punishes player 1 for offering too low. So this sort of ties is get tied to the cultural norms of sharing in various countries, and people find that in if you run this experiment in various contexts in various countries, you actually find you can test what is the minimum that one must share with with player 2 for to start accepting, right? You can play this game enough times to find out those thresholds in a particular context, and then people compare these thresholds across various contexts, say US or and India and sub-Saharan Africa, etc., and then they find that in some contexts these thresholds are very high. Often player 2 rejects relatively high offers, so unless it's 50-50 or something close to 50-50, player 2 often rejects in many contexts. But in other contexts, uh, player 2 is often ready to accept relatively small offer. Okay. Sometimes it depends on how player 1 got this rupees 100. Okay, so sometimes player two's rejection strategy in experimental lab setting is a function of how this rupees 100 is arrived at. So suppose before they play this game, in some cases experimenters have made player 1 work hard to earn rupees 100, and player 2 knows. In that case, people find that player 2 is much more accepting of a very unequal offer, because player 2 thinks that one has worked hard to earn rupees 100, so it's okay if he doesn't want to share a lot with me. But when player 1 wins a lottery and gets this rupees 100, then player two's threshold for acceptance, player 2 has becomes much more sort of strict in terms of sharing rules. Player 2 wants more egalitarian sharing rules, right? So these are the games you can nice things you can do with this game. But I wanted to show this to show how extensive form depictions look like for continuous time strategies. So let me stop here. In the next class on Thursday, I'll continue on the discussion of subimperfect Nash equilibrium. I'll do more examples and applications of that. Okay, so let me stop here now. Bye.